Hello all. In this video, we are discussing polynomial representation using linked list. An important application of the linked list data structure is to represent polynomials and their operations. Let us first look the general form of a polynomial. So this is a polynomial p of x. P of x can be generally written in this form. This an is the coefficient and this n is the exponent. An minus 1 is the coefficient, this n minus 1 is the exponent, etc. A1 is the coefficient and this 1 is the exponent. So this particular form is a general representation of a polynomial. So you can generally represent a polynomial like this. P of x is equal to an x raised to n plus an minus 1 x raised to n minus 1 plus etc. plus a1 x raised to 1. So when we know the examples of polynomials, we know that p is equal to three x raised to 4 plus 5x minus 2, or p is equal to 5x square plus 2x plus 1, or p is equal to 7x minus 3. Like that, we know the examples of a polynomial. So this is how a polynomial is generally represented. It is the sum of different terms and each term is of the form an x raised to n, where this is the coefficient and this is the exponent. Now let us look at the structure of a node to represent a polynomial. So here we know the basics of linked list. When we are defining the structure of a node for a polynomial, we have to keep in mind two terms. Inside a polynomial, we have, in a particular term of a polynomial, we have two things. One is coefficient and one is exponent. So these are the three fields in a particular term of a polynomial. So if you are representing each term of a polynomial as nodes in a linked list, each node will be having three fields like this. The first one is a coefficient field, second one is an exponent field, and third one is a next field. This next field is used to point to the next term in the polynomial. Now let us see how a node in the polynomial is declared. Struct polynomial node, polynode, and inside the bracket different fields of the polynomial term. Int coefficient, int exponent, struct polynomial node star, next. So this means the next is a field which points to the next node in the polynomial or in the linked list when it is represented as a linked list data structure. So this is how a term inside the polynomial is represented in a linked list. Now let us see how the polynomial manipulations are done. That means the different operations are done using the polynomial. So when the polynomial is represented using a linked list, the number of nodes to represent a polynomial is same as the number of terms in the polynomial. And a header pointer is used to point to the first node of the linked list. So here we have an example. P of x equal to 3x raised to 8 minus 7x square plus 14x raised to 3 plus 10x minus 5. So let us see how this is represented using a linked list. So one term consists of a coefficient, an exponent, and a next field. So this is the first term or the node for the first term. So its coefficient part, here you can see coefficient, exponent, and next. So the coefficient part of the first term is 3. The exponent part is 8. And we have the next part. This is the address to the next term in the polynomial. So let us see the next term. The next term is minus 7x raised to 6. So here coefficient part is minus 7, the exponent part is 6, and the next part points to the next node in the linked list or to the next term in the polynomial. So here the next term is 14x raised to 3. So in the next node we have 14, 3 and the next pointer. And let us see the next node. Next node is representing the next node in the polynomial, that is 10x. So 10x means 10x raised to 1. So the coefficient part is 10, the exponent part is 1. And it is again pointing to the next node. So what is the next node? Minus 5. This means minus 5x raised to 0. So the coefficient part is minus 5 and the exponent part is 0 and null, because there is no more term in the linked list. So this is the polynomial, and this is the representation of polynomial using linked list data structure. Now we have to discuss two operations in polynomials, addition and multiplication of two polynomials. So first one is polynomial addition. So consider two polynomials p and q. And we have to add those polynomials. P plus q should be the output. So r is equal to p plus q. R is the result variable. R is equal to p plus q. So p and q are two polynomials represented using linked list. And we have to add these two polynomials and we should get r as the output. This is another linked list. So for traversing purpose we can use a pointer p pointer to point to the nodes in P and q pointer to point to the nodes in Q. So we are going to discuss the polynomial addition. So this is the first polynomial p. P is equal to 3x raised to 4 plus 2x square plus 4x plus 8. So here we can see the linked list representation of this polynomial. Here in the first node 3 is the coefficient, 4 is the exponent. In the second node 2 is the coefficient, 2 is the exponent. In the third node 4 is the coefficient, 1 is the exponent. And in the last node 8 is the coefficient and 0 is the exponent. And here you can see q. Q is equal to 5x raised to 4 plus 7x raised to 3 plus 4x square. So here we have the linked list representation of q. And what we are doing is r is equal to p plus q. So this polynomial plus this polynomial is to be done. And what is the answer? 8x raised to 4 plus 7x raised to 3 plus 6x square plus 4x plus 8. How will you get this particular answer? So let us see the basics first. So this is the first polynomial, this is the second polynomial. So we will start a pointer, p pointer here and q pointer here. Okay, now the node, the exponent of p pointer is compared with exponent of q pointer. And we are checking whether it is equal or not. So first compare the exponents of the nodes which are pointed to by p pointer and q pointer. So the exponent part is the middle one, the red colored. So p pointer exponent and q pointer exponent. So we can see both are equal. So when the exponents are equal, we can add the coefficients. So we can add the coefficients 3 plus 8, that is p pointer coefficient plus q pointer coefficient. So 3 plus 5 we have 8. So we have to create a new node in the result polynomial. Create a new node. We have to add the term p pointer coefficient, this is p pointer coefficient plus q pointer coefficient, that is 3 plus 5 we have 8. Now what should be written in the exponent part? Exponent part is same for both, so either p pointer exponent or q pointer exponent. So here exponent is 4. So the first node in the polynomial is added, and in the first node we have the next part as null. Now addition operation is over, so we can move the p pointer to the next node, move the q pointer to the next node. Now compare these two exponents. Compare p pointer exponent and q pointer exponent. So here we can see p pointer exponent is 2 and q pointer exponent is 3. So we cannot perform an addition operation. Q pointer exponent is greater than p pointer exponent. So when we are adding it to the resultant linked list, we have to add in the descending order. So this particular node is to be added next. So q pointer exponent is greater, so we have to add this particular node to this result polynomial. So just make a node, a duplicate of this node, and add here. Okay. So the coefficient is copied 7 and the exponent is 3, and this particular field should point to this new node. Now the node from polynomial q is added, therefore we have to move the q pointer to the next position. Now check the q pointer exponent and p pointer exponent. So p pointer exponent is 2 and q pointer exponent is 2. Both are same. So we can do the addition operation. So what are added? P pointer coefficient and q pointer coefficient are added. So we can create a new node for that. So new node. So what is the value of this? This is a new node. We have to give values. So what is the value here? This is p pointer coefficient plus q pointer coefficient. P pointer coefficient is 2 and q pointer coefficient is 4. So it is 6 here. 6. And what is the exponent part? Both are same. So you can write p pointer exponent here or q pointer exponent. And you can point like this to the new node. Now after the addition to the resultant polynomial, advance the p pointer and q pointer to point to the next node. So p pointer is equal to p pointer next. So p pointer will reach here. Q pointer is equal to q pointer next. So it is actually null. Q pointer is null and p pointer is still not null. There are more nodes in the first polynomial. So since q pointer has become null, there is no need for comparing again. You can simply add the rest of the nodes of polynomial p to the resultant polynomial. So you can just add these nodes to the resultant polynomial. And this is our resultant polynomial. So this is our head, which is pointing to the first node in the sum of these two polynomials. So here you can see the answer is 8x raised to 4 plus 7x raised to 3 plus 6x raised to 2 plus 4x plus 8. So this is the result after addition of two polynomials. So let us explain how this is done. So there are three cases. Exponents of the two nodes or two terms are equal. In that case, we can simply add the coefficients and add it to the resultant linked list. You can simply copy the exponent. So this is how the nodes are created when the exponents are equal. Now next case is when the p pointer exponent is greater than q point exponent. So what happens is you can just add the duplicate of the current term in p to r and just advance p pointer to the next node. And case 3 is p pointer exponent is greater than q pointer exponent. Sorry, less than q pointer exponent. In that case, you can add the duplicate of the node pointed to by q pointer to the resultant polynomial r and then advance q pointer to the next node. So this is how the polynomial addition is done. So this is the algorithm for doing polynomial addition. Set p pointer is equal to p head, that is the first node. Q pointer is equal to q head, that is the first node of the polynomial q. And r head is equal to null. R head coefficient equals null. R head exponent equals null. We know that r is the linked list for the resultant polynomial. And r pointer is equal to r head. Now let us start adding the polynomials. So repeat until p pointer is not equal to null and q pointer is not equal to null. So first what we have to check is whether p pointer exponent is equal to q pointer exponent. If they are equal, what we have to do? We have to create a new node and we have to assign the different fields like this. The r pointer next is equal to temp. Temp is the new node created. R pointer is equal to temp. Now the coefficient part is p pointer coefficient plus q pointer coefficient. Exponent is same as p pointer exponent, or you can write q pointer exponent here. And r pointer next is equal to null because this is the only node. And in the other iterations also, the last node will point to the null. So in this linked list representation, you will always add new nodes at the end of the linked list only. So the newly created nodes next part will be null. And you can advance the p pointer to the next node and q pointer to the next node. Next case is if p pointer greater than exponent greater than q pointer exponent. In that case, create a new node. We have to just duplicate the p pointers node and add it to the resultant linked list or linked list. The next case is if p pointer exponent is less than q pointer exponent. In that case, you can duplicate a node of q pointer and just add it to the resultant linked list, and you can advance the q pointer to the next node. So this is how the polynomial addition is done. And even after these comparisons, if p pointer is not null, we have to add the remaining nodes to the r pointer, that is the resultant linked list, and we have to again check whether the q pointer is not equal to null. If it is not equal to null, we have to add the remaining nodes to the linked list. So this is how the polynomial addition is done in using the data structure linked list. So in our example, we already got the answer. 8x raised to 4 plus 7x raised to 3 plus 6x square plus 4x plus 8 is the sum of these two polynomials that we have considered.